because the score would be 0 if you have this. Well, SP implies SA. This is actually a negation. So yeah, basically this. So the score will be 0. So you are there. But the farther away, the more constraint missing, or the more incorrect are your numbers in this timing constraint, there will be a larger number. Okay. So yeah, that's so the goal is to give you an intuitive idea here, not to actually, show all the details. It will take more than an hour just to talk about this part actually. But I encourage you to look at the IEEE transactions paper last July. It gives you a lot of the information here, and there's some other conference papers at RTSS and RTAS, and there are description of the titles in my website, and they are abstract, but the actual link you can get it from IEEE or some of them from ACM, okay, from the digital libraries. Okay, so let's go back. There's some related work with incremental techniques, so I'm not claiming we're the first. But they have done this for other models, other languages, like mu calculus, and but not for real-time logic. So this is brand new for real-time logic. And also there's some discussion on the SAT problem and the incremental SAT. And of course, SAT was defined in 1971 by Cook. Okay, so we add, the tool allows us to add basically cycles, positive cycles, or which may be that could be created by adding one edge, or that could be changing some numbers. That could mean changing the constraints, or you may need to add several edges and nodes in order to create one. And as I said, if you have this junction of clauses, you need several cycles, and you need to build a search tree in order to be sure that you have a counterexample, and hence the original formula, the unnegated formula, is what you want. SP imply SA. Okay, so initially, you can obviously do this manually. So here we are proposing, of course, a mechanical tool that eventually can be fully automated. Okay, and here we are working on the specification, not on the actual code. But eventually, we want to do that to actual code or actual communication protocol in networking. Okay, so again, go back to the railroad crossing. And as I just mentioned, you can add new arc, new edges, or you can transform negative cycles. Okay. And the key point is the increment. Okay. So associated with each change, there's a cost. Okay. It's the increment, and of course, the closer it is to the theorem we want to prove SP implies SA, the better. So we'll choose that one. Sometimes there's a tie, or maybe there are too many choices. So we may have to pick at random. The more choices you have that have the same score, the domain expert would definitely help there. Because typically, if you wrote a program, okay, then there's a bug, and the system identifies it, very likely okay, this is what I did. Okay, so I fixed that. So I choose that particular choice. So definitely with the human domain expert, the developer, the tool will run much faster. Okay, so you have maybe the correct constraint much faster. But even if you don't have an expert, eventually, the convergence issue, so far the system converged. That's a question I get when I give talks at other places, is convergence. But so far we have observed that convergence it occurs 100% of the times with the test cases we have. There's some real test cases we just remove some formulas or maybe change some numbers, and it gets back to the basically the correct specification. And we also created synthetic formulas, and again the tool performs well. But we cannot say 100% sure. So that's another topic in itself, is proving the convergence. So I'm still looking for a student who is very theoretically oriented to tackle that issue. So we have a tool, and I can refer you to a website, and there's a link from my website, so you can actually run this and try it. So it's not like we just have a paper or papers, but you can try this tool. And you can download and try out the examples I have there. And the links is from my website. So this is an actual run of the system. Okay, and it shows this graphically. Okay, here it shows two crosses are missing. Okay, oops, right. And then it adds this crosses and in order to create positive cycles. All right, I think I'm going to skip some details on the choices of some of the parameters and go to the results directly, because I do want to spend some time on security, I think, because a lot of faculty members and students here are working on security, and that's why I added this bonus. Okay, because initially I sent David the verification talk, but I figured out, okay, even though security is not my main research area, lately I have basically some ideas of applying some of this work, real-time logic, in the security, in the modeling and verifying security protocols or intrusion detection systems.
In a way, if we can prove the system to be correct, then security issue is taken care of.
Oh, that's right. That would be hard, yeah. But that's the ultimate goal, and that's a good selling point if you can sell this to a client and say this is certified, with this. Okay, it's a guarantee. Yeah. Unfortunately, in the real world, there are far more constraints, far more uncertainties that you can model. That's basically the domain of input is infinite. So it's very hard to do that. But eventually we want to do that. Maybe on a certain piece of the protocol or IDS, the certain core of it. Okay, so this view graph just shows you the if you have 1, 2, 3, 4 constraints missing, and the time it takes on just a standard PC, not a supercomputer, to complete this debugging and verification. And this shows the numbers for in seconds for railroad crossing, the reactor, and also the X-38, which is the crew return vehicle for the International Space Station. This is a lifeboat to return astronauts back to Earth in the event of an accident on board, instead of sending a Russian spacecraft to retrieve them, which takes much longer. Okay. All right, so that's actually a prototype of this X-38. Unfortunately, right now this project is put on hold by NASA because of budget reason. So astronauts have to wait for the Russian, or maybe a shuttle launch, which is often delayed, right, to retrieve the astronauts if there are problems. And I think recently they have some, I forgot exactly the issue. It's oxygen or maybe CO2 detected in the capsule. So it could be serious, right? So this is something used to test the system, and we X-38, the part that we analyze is the scheduling part of the avionics. It uses 4-power PC for Byzantine agreement and for redundancy. And this is dropped high up in the air, and then it can return autonomously back to Earth. So this is a high-level view of our tool. So ADRTL is what we have, and then AD is the more advanced version that can basically do it almost automatically. Okay, so it's and then this basically telling you the old specification and incremental specification, and eventually we want to do this fully autonomously. Okay, future work. We want to basically, as I said, beside the autonomous thing, we are doing optimization. I didn't show it on this slide. And what happens if you have a platform, a processing platform, that is slower than what you have? So can it still, meet this specification? Because if it's slower, then your actions are going to take longer. Okay? If you are aware, power-aware computing, if you are familiar with that, if you run your laptop at a slower speed, then it takes longer to show your PowerPoint slides or run your applications. We like to basically combine this technique with scheduling, the scheduling research. Okay, I should acknowledge this is joint work with Stefan Andre and his group at the National University of Singapore, I think NSF, and also the Institute for Space Systems Operation. And these are some of the references